I'm really excited to be here. So excited that they had to tether me to the stage, or I'd sort of go off wild. No, more seriously though, why am I excited to be here? I'm excited because of what we just heard. There is truly a revolution taking place, right? And the people in this crowd, you're the guys that are making it happen. We spent. You heard I spent some time at Microsoft. We probably spent the last couple of decades digitizing most of the virtual products collectively. That's where a lot of the value creation happened. It gave us, companies such as Google, Netflix, Amazon, you name it, so that we can get things streaming. But what is happening right now is that is moving into the hardware world, and it's creating a lot of extremely exciting opportunities. When you all of a sudden put together these megatrends that are coming underneath, IoT, where all our products are getting smarter, composite materials that allow us to create shapes and flexibilities that weren't possible a couple years ago, 3D printing that allows us to take them and put them into production, and you put all of those things together, something truly remarkable is happening across hardware. That hardware and digitalization is coming together. And if you ask sort of the smart people that are trying to put a number on what is the amount of value that's going to be unlocked, they say something like $11 to $15 trillion. And just to put that in perspective, that's about the GDP of China in terms of value that's going to be created. That is what the amount of value that was created by the internet. And we all tend to sort of exaggerate revolutions in the short term and underestimate them in the long term. What do I mean by that? When I was at CERN smashing atoms, the internet had just come out. It was the early 90s. The first browser was actually written, for those of you who know the history, right at CERN. And there you sit and you're essentially sharing physics reports online, not knowing that 15, 20 years down the line, pretty much everything in terms of communications would run on an IP protocol. Right? Everything from the wireless network to the fixed network to the backbone of data across the world. Right? In the short term, we all thought that it would, everyone said, hey, this is going to revolutionize business. All the old businesses are going out of business. Did not happen. Right? The big .com burst, or bubble burst. But fast forward, those sort of mega trends keep working behind the scenes. And all of a sudden we're today where we pretty much take that for granted across the world. The same is happening with these megatrends, right? And that does not mean that it's perilous to be a startup, right? You can sort of hit that thing wrong. And that's sort of, that either sort of makes you hit or miss as an individual, but as a sort of collective, there's no stopping these forces. And the set of transition that's going to happen is going to totally astonish all of us in the long term. Just to give you sort of a couple of ideas of what's going on. Here's a quote that I love from General Electric, right? One of you'd sort of think is largest, most traditional set of companies that are saying, hey, over the next couple of decades, what's going to unlock value for us is being able to digitize. And they say they're going to be a software company. They're not going to be a pure software company, right? They're going to be a software company that blends it with what they're good at, which is producing fantastic pieces of machines. And they feel like, hey, over the last couple of decades, we've been on this 1-2% incremental path that is way different from these other disruptions that have happened. But they see that that's coming to their industry. Just to give you one example that I'll try to weave through some of it, just outside of Pittsburgh, where Ansys hails from, GE has built their first additive manufacturing pilot plant. And one of the first things that they took into that additive manufacturing plant was the nozzle for their jet engine, a highly complex, intricate piece of material that determines how the fuel gets into the jet engine and gets combusted. Used to be 18 different pieces of metal, essentially, that was put together, right? When you do stuff subtractively, you can't do cavities in one piece, right? That's why we have bolts. You do two halves and you bolt them together to get a chamber. In 3D, you can just print it, right? So they can now print these intricate geometries that weren't possible before. So they took 18 different parts in this very sensitive piece of material or sensitive piece of equipment down to one piece, printed geometries that you weren't able to do before. And not just was the piece of material itself lighter, but the way it acts with the rest of the systems allowed them to reduce fuel by 15% and CO2 emissions by 15% out of a jet engine. That is quite remarkable, right? From 3D printing, from being able to do all the other things around it that brought this together. And that's why they're so excited about it. Plus, on top of that, I would argue that the stuff that, at least for those of us that are keen about physical things, right, not just digital things, but physical things, the paradigm for the last couple of years has been, let's outsource everything, right, and get the production costs down. And that's great, right? That gives all of us nice and affordable pieces of equipment, but it's not a true revolution. Right? It was mainly the same production methods, just at a lower price. But that paradigm is running out of fuel. This graph shows you the blue line is the annual labor cost in China, and the black line is the annual sort of roughly equivalent cost of a robotic factory. When I was a kid, everything was made in Japan, and that was cheap. Right? Fast forward to today, and made in Japan is not cheap, right? That's high quality. And China will have to figure out how to compete in a similar world, because their low cost advantage is running out of space, and the ability to do things local, like in an ecosystem like this, and get to market quickly is just on the rise. And that's, again, one of those mega trends. And what happens when all of a sudden manufacturing becomes local? When you can sort of source whatever you need in a local ecosystem, when you can do mass customization. If you used to produce a car, it costs you millions of dollars to change the production line. That's why we get these massive sort of, if you want, car series where there's millions and millions being produced that are essentially identical vehicles. It's so expensive to change your production line. It's also pretty expensive to develop a new car, but that's a sort of a different thing. But with this, it'll be thousands of dollars, very shortly to change a production line. So what happens when a car becomes like a fashion statement, right? When they last for 6 months, and then you better be on to the next thing that you want to wear, right? Because it's already out of fashion, or you want to tweak your car. That totally disrupts a value chain. You might laugh, right? But sort of previously, some of the people that were doing clothing and so on also outsourced everything to China, but that gives you 6 months supply chains. And when you have things like fashion that is fickle, right? If you fail, if what in the ship is on the way to your stores is already out of fashion, you're just sunk. You have no ability to change flexibly. And that's what's going to happen, over the next couple of decades to pretty much everything that's going to be manufactured, is that we have that type of agility to change very, very quickly. Now, unfortunately, that comes with a price. So all of these things, all of the revolutions are wonderful, at least in fantasy land. But as someone I talked to said, hey, getting an innovation to market is really, really expensive. I have to do all these tests. I have to, check all these things out. Yeah, the number, if you want, and I don't want to simplify, but it used to be simple because I had a fewer set of choices. My piece of sort of equipment, is it aluminum or stainless steel, right? And then I take it to a CNC machine, and I'm sort of done. Again, I'm really, really simplifying, so apologies for those of you that have been there. But when you add composite materials, right, you now have thousands of different materials to choose from. The way you bond them, which glue you use, all changes the properties. You can print them out into shapes you never had before. You're now putting a chip on board that was never on board, say a pump or an electric circuit breaker or whatever it is, right? So you now have to have a chip on board. That chip has to have software. It's probably wirelessly connected. Everything else is wirelessly connected, so now they're interfering with each other. How do you make sure that you have signal integrity? The complexity is orders of magnitude than it was before. So if you want, the price of the new world is complexity. And when we talk to our customers and engineers, which is what you see on the right-hand side, apologies for not being too legible, but when you ask engineers, what's the top product challenge? They say two things. It's the complexity of the product itself, and it's the complexity of the environment in which I'm going to put it into. Right? And on the left-hand side, you see some of this complexity, illustrative, just the lines of code. A Ford F-150, the most popular truck, now have more lines of code than your favorite operating system and more lines of code than a jet fighter. Come on, what world are we living in when a standard pickup truck has become that complex, right? And when that all of a sudden is for an auto manufacturer, one of the key differentiating factors, right, is how do I bring my product to life in code? But that is the world we're in, and that's the cost of complexity. Now, I know that I'm biased, but I'll tell you that the simulation will help tame some of that complexity. This shows you some of the studies we've done on customers that use simulation for producing products versus not. You get something like 9 times faster time to market for a 4x of the production cost. And when you ask engineers what do they think will revolutionize product development over the next 5 years, you see simulation sort of neck to neck with 3D printing. Now, why can that be the case? Well, let's go back to that GE fuel nozzle that I spoke about. Most of the geometries inside this fuel nozzle, right, that gives optimal performance of the jet engine, those geometries are thinner than our human hair, right? That's how small they are. It's now one integrated printed piece. There's really no way to test it. You can't put any sensors inside it. Put a sensor inside something that has geometries that's less than our human hair, and you totally distort all the effects that you're trying to measure. So all of that is simulated. 100% simulated to figure out, and then once you've figured out what you think the optimal configuration is, of course you take one of them out, test it, and see whether it sort of performs the way you'd expect it. But up front, all of it was simulated, and there was no way you could have done that if you couldn't very accurately determine what the flow is, what the combustion rates is, what the temperatures are, what the distortion of the metal is under the different pieces of pressure. Even the manufacturing method, right? When you 3D print metal, and you heat and cool it with a laser, that creates stresses, right? Those stresses warp a piece of metal. So you might think, hey, I'm printing this nice CAD file I have, but what comes out is a slightly warped form, right? So you're not getting the exact geometry out, and you're also getting something that will have increased metal fatigue, because it has these inherent stresses in it. Now you can simulate and you can say, hey, what's the anti-deformed shape, so to speak, that I need to print so that as I print it, it comes out and it warps into the exact shape that's needed. And it reduces the residual stress in such a way that it actually is meaningful and comes out. So that's sort of the journey that we've been on for the last 40 years, if you want, at ANSYS, is building all the physics simulation that allows you not just to simulate the structural integrity of something, as I just talked about, but also the flow, the heat, the electromagnetic radiation, the instruments, the cooling, the power profiling. You can now run simulation, for instance, on a chip with the actual workload, with the code that it's going to run, and say, don't just give me sort of a general optimization of least amount of power in a chip. Give me an example of the specific stuff that's going to happen in this chip during boot up and runtime, so that I can put it on something and it can run right for months and months on battery power, or reduce the amount of CO2 that a building like this is taking out. So it's truly sort of going across, and not just the individual components, but how do I string them together? Back to this complexity, right? How do I take the individual components and see how they work in the bigger and simulate that as well? So that before you start building your first prototype, you've already explored a huge space of design options and brought to place. So what we're seeing right now is a lot of companies in this sort of middle bubble have actually built digital prototypes over the last 10, 20 years, right? Simulation is not new to GE, as an example. They've been simulating for multiple years, but what they typically did was come up with a design, go through the design, have a final design, and then simulate to see whether it, to validate it. What is happening right now that I'll give you a couple of examples of is because of the computing power and everything else, because of the ease of use of these things as sort of all software becomes easier to use and faster, we're seeing it move up front. So instead of coming up with a design and then simulating to figure out whether the design does what you want it to do, it's being turned upside down. And people are saying, let me just sort of put the parameters into the system and give me the design that optimally fulfills whatever I want to do. A lot of the companies we work with say, hey, we make some assumptions early on that actually locks other people into a small box further down the production process, instead of being able to simulate the entire system and give everyone degrees of freedom. And then they run hundreds of thousands of simulations with different parameters to see which one is the optimal for what I want to bring to market. And we're also seeing things go downstream into production. So as an actual piece of machinery is running with all the sensor data, you're sending that into a simulation saying, how can I optimize? How can I run more energy efficient or whatever it is in real time, back. So those are some of the things that we're seeing that we think will help with some of these other megatrends in capturing that complexity and helping you guys bring your ideas to market. So let me just give you a couple of examples and start getting concrete instead of this sort of abstract talk. There's a startup here in San Francisco, Nebbia. They came up with an idea of a shower head that saves 70% of the water. Essentially what they do is atomize the water. So you're sort of in this mist. And when I first tried it, I thought, this is going to be a little unfulfilling, right? I'm only getting 30% of the water. I like a good, nice shower, but it actually feels exactly as being in a real shower. Now the problem, unfortunately, is when you atomize water and when you get smaller and smaller droplets, they lose heat faster, much faster. So you can save 70% of the water, but you're going to take a cold shower. That's not a sort of very good value proposition in sort of mass market. And they'd been going back and forth with their local machine shop building the prototypes, right? Took about a week. Hey, let me sort of change the configuration of the nozzles, see if that improves the design, put it up in their shower in their own apartment, test it out. Did this feel, hotter or colder, right? And every one of those iterations took about a week back and forth, right, in building the actual physical prototype, testing it out. They built a computer model, right, took sort of the software that we had developed for the GEs of the world or the SpaceXs to do sort of high turbulence and fluids models, modeled the shower head, and they were able to run 2,000 iterations of different designs over a week. And instead of going 2,000 weeks back and forth, they then had sort of, hey, this is the optimal configuration of the cone of water that traps most heat in the actual cone, right? And they use that, and then a couple of more iterations after that of physical prototypes, and they have the product that is shipping right now. I'm hoping to install the one that I get very shortly, because I have a teenage son that loves to take 15 to 20 minutes long showers in the morning, and I want to cut that water consumption down by 70% for sure. But that's just sort of an example of what I meant with digital exploration, right? You take it up front and you say, what if? Right? Multiple thousands of different iterations in the computer instead of having to build yourself through physical prototypes in something that is a very, very quote-unquote simple mechanical system, right? This is sort of fairly non-complex. All the secret sauce is hidden into the nozzle, right, and the actual configuration of the nozzle in the shower head. But as you look at sort of more complex IoT systems, the same thing is true, right? And more complex, from building the chips to the antennas to the sensors to the power management to the vibrations that your motherboard or your PC board will have, all the way over to the embedded software development. All can benefit from exactly the same thing. And just to give you a couple of examples of that, here's sort of an example of some key customers and what they've gotten out of it. As I mentioned, being able to simulate the actual power flow, both in your chip as well as on your PC board, and say what is the optimal configuration. I mean, again, when I was a kid, soldering a PC board was a relatively simple thing. These multi-layered, super thin things of today are pretty complex things, and figuring out how do I get signal integrity into those. And by the way, all the way over to the mechanical, it turns out, of course, that heat is dissipated throughout your PC board. Guess what the number one issue with most PC boards and IoT connected devices are? Warping from the thermal heat that breaks some of these thin connections. You're able today to simulate that entire workflow and say, hey, I have a chip, I have a set of components, here's the heat dissipation on my actual PC board, what's the warping, where should I be considering breakage of the individual traces, right, and getting it to work. You can simulate not just sort of the actual antenna itself, you can simulate the environment, you could build sort of a whole cityscape or whatever it is, right, with interfering antennas and simulate and say, how do I get signal integrity, how do I get power? And you get things like this, being able to either increase antenna range by 5x, or the Vortis example is actually the inverse, saying, hey, I need this, but how can I increase my battery life by reducing the amount of power that goes into the antenna that's on all the time, right? PC boards, again, that sit and vibrate, if you put them on a truck or whatever it is that you're putting your PC board on, a pump, a piece of electrical equipment. How can I, if you want to try to run typical simulations like that, right, you have to put thousands and thousands and thousands of hours into it to see that they actually hold. You can also build virtual prototypes of that for fatigue testing, for drop testing, and so on of your pieces of equipment. And all the way over to the software that in an Airbus runs the entire cockpit is actually also simulated. And what do I mean by that? I mean that they built a system model, and then out of that system model, the embedded software that runs that entire system was auto-generated, right? Zero code defects. That the cockpit and the associated control system in an Airbus, luckily, have never crashed or blue screened or anything else like that, right? And if you think about the millions of lines of code, if we sort of humanly program them, what is the chance that we introduce an error in mission critical systems like this? Pretty high, versus being able to simulate and say what happens in the physical systems that interacts with the software systems, and once I've verified that system, can I produce the code that verifiably produces exactly the same results in production, right? So that's if you want, the power of simulation that hopefully can help you. But as I said, it's not just being used today in product design. We see it going into production. This is to give you an example of some of the early systems we're working with where, and I simplified a little bit, but this example is from a windmill park, right? You have a number of windmills in production. Typically, they sit in giant rows, behind each other. Once the wind changes direction, what is the turbulence from the front one to the next one to the next one? How can I change the angle or rotation of the individual blades in such a way that it gives optimal? So what they're testing right now is, can we send that back in, run a real-time simulation? Sorry, this used to animate. Never mind, there was a sort of 3D simulation in the background that was supposed to show up in an animation. Never mind, you can sort of imagine it, right? That the computer model crunches all of that in the background and says, hey, dear operator, if you do these and these and these configurations of your windmills, you're going to get the optimal power out of that. I've spoken to some of the people. This is going into big machinery to begin with, because today it's still, if you want, relatively expensive to both build these models and get it back. So it's going to be a while until we're, before our Fitbit benefits from a simulation. But it's equipment, like windmills, like in this example in the partnership we have with GE, where it's building, a full what we call a digital twin of a gas turbine, to say, given this particular gas turbine under its operating loads with all its sensor data that's coming out, how do I optimize that? And they estimate that will save about 200 million for an average gas turbine. There happen to be a ton of those gas turbines out there, which amounts to some ridiculous $70 billion of annual increased production in power plants by being able to do that dynamic monitoring and back again. So that was hopefully sort of giving you a little bit of inspiration in terms of what can simulation do to help you in product development. Harness, as I said, it's already something that most of the big companies across different industries are using in their product development. But the nice thing about all of these things becoming easier to use is you do not need to be a rocket scientist yourself and know all of the intricacies of a turbulence model or of mechanical fatigue and cracking or of electromagnetic propagation anymore. Right, it used to be that way, but the software has become much easier to use. And in fact, I'm really happy to say that we really would love to see what you can do with it. We put together a startup program for that to put the power of the software in the sort of hearts of an entrepreneur, as it was mentioned. I used to be an entrepreneur myself, and there are times in your life where you can go to GE and say, hey, guess what? You can save $200 million per gas turbine. Yes, then you should pay $50,000 for our piece of software. That kind of makes sense. But if I don't have $50,000, which is certainly where I was when I was a startup, that's not really a value proposition you can do anymore. And we'd love for you to benefit for it. So we put together a startup program that allows you to almost free of cost to take advantage of this, get started, see whether simulation works for your company or not. And hopefully all of you will visit the booth and take advantage of that. And then just sort of before I end, let me give a plug if you want to hear more. Eric Miller's here. He's giving a speech later around simulation. He's one of the most knowledgeable guys in terms of how you can actually take that and implement it into your product development. So go visit his session and get even more inspired.